Right now, even as you sit still, the universe is moving around you. Beneath your feet, the Earth completes a full turn every 24 hours, carrying everything on its surface eastward at more than 1,600 kilometers per hour. The moon silently loops around us, pulled by gravity into a dance that has lasted billions of years. Together, Earth and Moon sweep around the Sun at nearly 30 kilometers per second, fast enough to cross the entire planet in the time it takes to drink a cup of coffee. But even the Sun is not standing still. It is racing through the Milky Way, orbiting its center like a glowing ember caught in a vast current of motion. Look up at the night sky and it may seem frozen stars fixed like silver pins on a black dome. But this stillness is only an illusion. Every star is drifting. Some surge forward at speeds greater than bullets, while others crawl like glaciers. Their trajectories twist and weave across the galaxy, reshaping constellations that we take for granted. A few 100,000 years from now, Orion and the Big Dipper will no longer exist in their familiar forms. The stars that shape their outlines will have moved on, drawn into new patterns by their invisible orbits. Even galaxies are not immune to this grand choreography. Our own Milky Way is hurtling toward a massive gravitational center, the Great Attractor, along with thousands of other galaxies, from the smallest grain of dust to colossal clusters stretching hundreds of millions of light years. Everything is caught in the same cosmic current. Motion is not the exception, it is the rule. And perhaps the most humbling truth is this: you have never truly been still. Every second of your life has been spent moving through a universe in constant rotation, orbit, and drift. The quiet room you're in is riding on an enormous invisible wave of motion that began billions of years ago and has never stopped. The deeper we look, the clearer this pattern becomes. Every world turns, every star revolves, every galaxy curves around something greater than itself. It is as if the universe is built on a hidden rhythm, a quiet but unstoppable pulse that reaches from the tiniest atom to the largest structures we can imagine. It is not chaos, it is choreography. When astronomers map the night sky, they are not just drawing constellations, they are tracing orbits, rotations, and flows of matter shaped by the pull of gravity. The orbits of planets are predictable, following elegant curves like dancers repeating ancient steps. But step further out and that graceful motion becomes vast and astonishing. Whole star systems swirl around the galactic core, and the galaxy itself travels along enormous gravitational filaments that stretch across the cosmic web strands of matter, spanning hundreds of millions of light years. This quiet ballet is the universe's natural language. It governs how matter gathers, how structures hold together, and how energy moves through space. It is why planets flatten at their equators, why stars burn steadily, why galaxies form spirals instead of collapsing into formless clouds. Without this invisible rhythm, the cosmos would be unrecognizable, a universe without structure, without direction, without time as we know it. And the most remarkable part, none of this movement was set in motion by some external hand. It is not an afterthought of creation. This motion was there from the very beginning, written into the fabric of the universe itself. What began as the faintest twists in the newborn cosmos has grown into a grand universal dance that carries everything, including us. Every layer of the universe tells the same story, a story of motion. If you could step outside our galaxy and look down upon it from above, the Milky Way would not appear as a still picture. It would resemble a luminous whirlpool, stars gliding along curved lanes as if painted by invisible hands. Further out, clusters of galaxies circle shared gravitational hubs, and beyond that, filaments of the cosmic web stretch like threads pulled taut by time itself. This is not random drifting. It is organized, consistent, and ancient. Scientists sometimes describe this cosmic motion as a kind of fossil record. Every rotation, every orbit, every curved path is a trace of an earlier event, the imprint of energy that was set in motion long before stars ever formed. Just as wind leaves ripples on water, the early universe left its signature in the way matter moves today. We are not observing accidents. We are witnessing memory written into the structure of space. What makes this story powerful is its universality. From electrons spinning in atoms to galaxies wheeling through the void, motion connects everything. It is a thread that runs through all of physics, linking forces, matter and time. And somewhere at the root of it lies a moment, the first turn, when this entire cosmic dance began. That is where our journey now leads, to the birth of motion itself, long before planets formed, long before stars burned, the universe itself began to move. In the first fraction of a second after the Big Bang, space was a storm of quantum fluctuations, minute ripples in the fields that filled all of reality. These ripples were not still. They twisted, folded and looped, creating the earliest hints of rotation in the newborn cosmos. What we now call cosmic motion wasn't added later, it was already there, woven into the geometry of space itself. Then came a dramatic transformation, a burst of inflation that expanded the universe faster than light could travel. Those tiny twists, once confined to the subatomic scale, were stretched across immense cosmic distances. Microscopic eddies became the seeds of colossal flows. It was as if the universe took a single breath, and in doing so scattered its original motion into every corner of existence. The quiet revolutions of today's stars and galaxies are echoes of that moment. As the young cosmos cooled, energy condensed into matter. Quarks joined into protons, and neutrons and electrons began to orbit around nuclei. But these particles didn't form in silence. They carried the memory of those first rotational imprints, moving in ways set by the earliest conditions of reality itself. Every atom that would one day build stars, worlds, and life already bore that ancient rhythm. Motion wasn't an accident of the future. It was the first inheritance of the universe. To understand why motion appeared so early, we need to look closely at the laws of physics that were born with the universe. In those first fleeting instants when everything was compressed into something smaller than a grain of sand, even the tiniest fluctuations mattered. A subtle asymmetry here, a small imbalance there. These microscopic twists were enough to change everything. When space began to stretch at unimaginable speed, those tiny rotational signatures were frozen into its structure like fingerprints pressed into wet clay. The result was a universe with direction. Some regions carried slightly more angular momentum than others, shaping how matter would later collapse and swirl together. These weren't deliberate patterns, but natural consequences of physics itself. From that point forward, every cloud of gas, every star, every galaxy that would ever exist inherited a fragment of that original motion. The first eddies became rivers, and those rivers became currents that continue to flow today. This is why, when we study the large-scale structure of the cosmos, we see patterns too vast and organized to be accidental. The same rotational bias that existed in the first fractions of a second after the Big Bang still echoes through the shapes of galaxies billions of light years away. The universe remembers how it began, and that memory is written in motion. The universe didn't have to learn how to move. It was born moving. From the instant space and time came into being, motion was part of their foundation. Not an external force, but a property of existence itself. That is why even the smallest quantum fluctuations became the architects of structure. When inflation stretched those patterns across the cosmos, they became a permanent part of the blueprint of reality. Every orbit and rotation we observe today is the echo of that ancient beginning. Over time, these subtle flows grew more pronounced. Regions of space carrying slightly different angular momentum pulled matter into spiraling motions, guiding it toward forming the first stars and galaxies. None of this required a push or a spark. It was the natural unfolding of what was already set in motion. This is the secret written into the fabric of the cosmos. Motion does not vanish. It transforms, grows, and shapes everything that follows. And at the heart of that truth lies one of the most elegant and unbreakable rules in all of physics, a law that ensures the universe keeps turning. That law is the conservation of angular momentum. When something begins to move, it wants to keep moving. This idea is simple but profound, and it's the foundation of the cosmos. In physics, we call it the conservation of angular momentum, a law that has never once been broken. It tells us that once rotation begins, it doesn't just fade away. It persists shifting and transforming, but never disappearing. Imagine a figure skater pulling her arms close to her chest. As she does, her spin quickens. She isn't creating new energy, she's redistributing what's already there. The same principle governs collapsing clouds of gas in deep space. When gravity draws matter inward, its rotation speeds up, tightening into a vortex that can give birth to stars and planets. A small initial twist can grow into a storm of cosmic scale simply because the universe is faithful to its own rules. This law doesn't just explain how motion continues, it explains why the universe has structure at all. If angular momentum could simply vanish, stars would stop spinning, planets would slow to stillness, and galaxies would collapse inward. But that doesn't happen. The universe remembers every turn. The beauty of this principle lies in its universality. It works for a skater on an ice rink, for a swirling hurricane, and for a galaxy spanning 100,000 light years. One law written into the fabric of reality holds it all together. This single rule connects the smallest and largest scales of existence. An electron spinning within an atom, a planet turning round its star, and a galaxy revolving in the cosmic web are not separate stories. They are different verses of the same law repeated across the universe. No matter how far apart they are in size or energy, they all obey the same rhythm. Motion can change its form, but it cannot be erased. Think of a collapsing cloud of gas in a star-forming region. At first, it may be almost still just a faint drift of particles in the dark, but even the tiniest irregularity is enough to create a slight turn. As the cloud contracts, that subtle motion amplifies, forcing the gas into a disk that flattens like a spinning coin. At the center, a star ignites. Around it, rings of material orbit like threads woven by an unseen hand. What began as a whisper of motion becomes the architecture of a solar system. This is not just a story about stars, it's a universal blueprint. Galaxies emerge the same way. A faint imbalance amplified by gravity blossoms into vast rotating structures, stretching tens of thousands of light years. Even the delicate spirals of galaxies like the Milky Way are simply the natural consequence of angular momentum conserved over billions of years. It's almost poetic. The universe does not waste movement. It recycles it, passing it from one scale to the next, weaving it into everything that exists. Even when systems collide or break apart, the law remains untouched. When two galaxies meet, their stars rarely smash directly into each other, but their rotations combine like merging currents in a river. Angular momentum is shuffled, rebalanced, and passed on to the newborn structure that emerges after the chaos. It's why galaxies can change shape without losing their motion. The pattern may evolve, but the rule stays unbroken. The same is true on smaller scales. When asteroids collide, when stars interact in binary systems, or when black holes spiral toward one another, momentum is never destroyed, only redistributed. It's as if the universe is a perfect accountant keeping track of every turn and every orbit with flawless precision. This unyielding law is what gives the cosmos its continuity. It ensures that the motion seeded at the beginning of time still lives on, today guiding the formation of worlds, the birth of stars, and the shape of galaxies. It is one of the simplest and most elegant principles in nature, and one of the most powerful. In the next part of our journey, we'll follow this law into familiar territory. The worlds themselves, planets and stars, are not just passengers in this cosmic current. They are among its most beautiful creations. When we look at planets and stars, we are seeing the fingerprints of ancient motion made solid. Every world carries the momentum it inherited at birth. In the beginning, planets form inside vast disks of gas and dust swirling around young stars. Gravity pulls matter inward, but angular momentum forces it outward, shaping the cloud into a flattened, rotating plane. This delicate balance is why planetary systems, including our own, are built like cosmic clockworks with worlds orbiting along nearly the same plane in the same general direction. Take Earth as an example. Our planet turns once every 24 hours, creating the cycle of day and night. That steady rhythm isn't arbitrary. It's the lingering spin from the rotating disk that birthed the solar system billions of years ago. Jupiter spins even faster, completing one turn in just 10 hours. Its rapid motion amplifies its equatorial bulge, distorts its shape and fuels colossal atmospheric flows, including the Great Red Spot, a storm so vast it could swallow Earth whole. These rotations aren't just curiosities. They control weather patterns, generate magnetic fields, and define the daily heartbeat of entire worlds. Without rotation, the sun would scorch one side of a planet while the other froze in darkness. Instead, turning worlds share their heat, mixing air and water in endless cycles. In every planet and every star, this ancient rhythm persists. It is the whisper of the disk that made them the memory of a universe that began in motion and has never stopped. A planet's rotation is far more than a mechanical detail. It is a powerful engine that shapes its destiny. When a world spins, it creates a rhythm that governs air, water, and temperature. Earth's steady rotation gives us a 24-hour cycle, dividing the planet into alternating periods of light and darkness. That cycle fuels winds, currents, and storms, driving the entire climate system. If Earth turned more slowly, days and nights would stretch endlessly. One hemisphere would bake under constant sunlight, while the other would freeze in perpetual night. Life as we know it would struggle to adapt. The influence of rotation extends beneath the surface too. Deep within our planet, molten iron moves in spiraling flows. Combined with Earth's rotation, these flows generate a powerful magnetic field, an invisible shield that deflects harmful solar radiation and protects our atmosphere from being stripped away. Without this magnetic cocoon, Earth could resemble Mars. Cold, thin-aired, and vulnerable, stars obey the same principles. When a massive cloud of gas collapses to form a star, its rotation determines how the newborn star behaves. Faster rotation leads to stronger magnetic fields and more intense stellar winds. It sculpts the shape of the star, influences its activity, and even affects the formation of planets around it. From the surface of a rocky world to the heart of a star, the universe writes its story in motion. The diversity of rotation across the solar system tells a story of inherited motion and the scars of cosmic encounters. Mercury spins so slowly that one full day lasts nearly 2 Earth months. Venus turns in the opposite direction from most planets, its thick atmosphere swirling in a perpetual sluggish storm. Mars spins at almost the same pace as Earth, giving it familiar day lengths but a far more fragile climate. Then there is Jupiter, a giant that completes a full turn in just 10 hours. Its rapid motion whips its atmosphere into violent banded jet streams, carving storms that rage for centuries. These differences are not random. They are records of how each world formed and evolved. Impacts with other bodies, gravitational interactions, and the way mass was distributed during formation all left their mark. Even our moon carries this memory. It turns exactly once for every orbit around Earth, keeping the same face pointed toward us. This perfect balance tidal locking is the result of billions of years of gravitational tugging slowly synchronizing its rotation with its orbit. Stars too bear signatures of their birth. Young stars often rotate much faster than their older counterparts. Over time, they lose angular momentum through stellar winds and magnetic interactions with their surroundings. This gradual slowing is like a cosmic heartbeat, allowing astronomers to estimate a star's age by measuring its rotation. In this way, motion itself becomes a kind of clock, one that has been ticking since the dawn of time. The spinning worlds we see today are not just moving objects. They are living archives of cosmic history, each rotation a line written in the story of the universe. In most places, rotation shapes worlds gently, but in the deepest, most violent corners of the universe, it pushes the laws of physics to their limits. Nowhere is this more striking than in the strange realm of neutron stars, the collapsed cores of massive stars that once burned bright. When such a star runs out of fuel, its outer layers explode outward in a supernova, while its core collapses inward. In the span of a heartbeat, something the size of a star shrinks into an object barely 20 kilometers wide, but it keeps nearly all of its angular momentum. The result is staggering. A neutron star can turn hundreds of times every second. These ultra-dense objects are like cosmic lighthouses. As they rotate, powerful magnetic fields channel beams of radiation that sweep across the universe like clockwork. When one of those beams crosses Earth, we detect it as a pulse, a perfectly timed flash repeating again and again. That is why these stars are called pulsars. Some of them are so precise that they rival atomic clocks, keeping time more steadily than any machine built by humans. The physics behind this is simple but awe-inspiring. When something contracts drastically but keeps its momentum, it must rotate faster. It's the same principle as a spinning skater pulling in their arms, but amplified to cosmic extremes. The difference is scale. Here, a collapsing star doesn't just turn faster. It becomes a spinning remnant so dense that a single teaspoon of its material would outweigh mountains. This is rotation pushed to its most unforgiving edge. Beyond neutron stars lies an even more extraordinary phenomenon, the rotating black hole. Unlike ordinary matter, these objects don't just sit in space. They pull space itself into their motion. When a massive star collapses completely, or when black holes grow by swallowing matter, they can accumulate tremendous angular momentum. What emerges is known as a Kerr black hole, a kind of cosmic vortex where space and time are no longer separate stages but part of a single twisted fabric. Near a rotating black hole, this twist becomes impossible to ignore. A region called the ergosphere surrounds the event horizon. Not a physical surface, but a boundary where space itself is dragged around faster than anything can resist. Inside this zone, even light cannot remain still. Every particle, every photon is forced to follow the spinning geometry. It's as if the universe itself has become a whirlpool, pulling everything into a one-way flow. What's remarkable is that this rotation isn't just a side effect, it shapes how the black hole behaves. Through a process called the Blandford-Znaiec mechanism, the rotational energy of the black hole can be converted into powerful jets of plasma, blasting out into space for thousands of light years. These cosmic jets are among the most energetic events in the universe. They are not powered by falling matter alone, but by the black hole's own stored angular momentum. At this scale, rotation is no longer just motion, it is a force that bends reality. At these unimaginable scales, rotation stops being something we merely observe. It becomes a fundamental force shaping the behavior of space and time themselves. Near a rapidly rotating black hole, time stretches and warps. An object caught in its grip doesn't just orbit. It's carried along by the very geometry of space-time, twisted like leaves in a whirlpool. The faster the black hole turns, the more extreme this effect becomes. In the most violent cases, the surrounding space is spun up to a significant fraction of light speed. This boundary-pushing motion isn't just theoretical. Astronomers have observed its fingerprints in real data. Using X-ray telescopes, they've measured how matter accelerates in the disks surrounding black holes. Using radio interferometry, they've imaged the bright ring around a shadow, a direct consequence of light being dragged by rotation. And through gravitational wave detectors, they've heard the spin of compact objects colliding, encoded in the ripples that spread across the cosmos. When motion reaches this level, familiar rules begin to bend. Time slows, light curves, energy can be extracted from the spin of a black hole itself, launching jets that tear across intergalactic space. These aren't just natural wonders, they're windows into the deepest structure of reality. They show us that rotation isn't a minor feature of the universe. It is a force capable of sculpting space-time itself. The idea that everything moves might sound poetic, but it's not just theory, it's something we can measure. Centuries before modern telescopes, humans found ways to see motion that isn't visible at a glance. One of the most elegant proofs came in 1851 when a French physicist named Léon Foucault suspended a massive pendulum beneath the dome of the Pantheon in Paris. Once set in motion, the pendulum swung back and forth in a perfectly straight line. But as the hours passed, something extraordinary happened. The direction of its swing appeared to slowly rotate. The pendulum wasn't changing course, the Earth was turning beneath it. This quiet experiment transformed an abstract idea into a visible truth. For the first time, people could see the rotation of our planet not through distant stars or complex math, but through a simple weight hanging from a ceiling. It was a moment of clarity. The ground beneath our feet is never still. In the decades that followed, astronomers turned their gaze outward. They tracked shadows sliding across Jupiter's cloud tops, watched sunspots drift along the surface of the sun, and measured shifts in starlight caused by rotation. The colours of light shifted slightly blue when moving toward us, red when moving away, a subtle signature of motion known as the Doppler effect. With these tools we learned to read the universe like a clock tracing movement from worlds we could never touch. As technology advanced, our ability to observe motion deepened. In the 20th century, radio telescopes began picking up signals from neutron stars, pulses so precise they arrived like the steady tick of a perfect clock. These cosmic lighthouses proved that stellar remnants were spinning hundreds of times per second. No longer were we limited to watching planets and stars with visible light. We were now listening to the universe announce its motion across vast distances. Then came a new generation of observatories. X-ray telescopes revealed the blistering disks of gas orbiting black holes heating up as they whirled at extreme speeds. Infrared instruments traced the rotation of dust-enshrouded stars hidden from optical view, and missions like Gaia mapped the motions of over 1 billion stars in the Milky Way, with exquisite precision recording subtle wobbles and orbits that would have been invisible a century ago. But perhaps the most astonishing evidence of all came from a kind of observation we once thought impossible, not light, but gravity itself. In 2015, LIGO detected gravitational waves, ripples in space-time created when two black holes merged. Encoded within those waves was information about their spin, their mass, and their dance before collision. For the first time, we weren't just watching motion, we were feeling the tremors of the universe turning. These discoveries left little doubt. Rotation isn't a rare feature. It's everywhere at every scale, waiting for the right instrument to reveal it. What makes these observations so powerful is their consistency. No matter how different the methods, a swinging pendulum, a shifting wavelength, a burst of X-rays, or a ripple in space-time, they all tell the same story. Everything moves. From the slow turning of planets to the furious whirl of black holes, motion is written into every corner of the cosmos. We don't just infer it. We can measure it, trace it, and even predict it with astonishing accuracy. Each technique opens a new window onto the same truth. Pendulums reveal Earth's rotation beneath our feet. Telescopes capture planets and stars spinning in distant systems. Radio arrays listen to pulses beating like cosmic metronomes. Gravitational wave detectors catch the final spins of colliding black holes. Layer by layer, the picture becomes clearer. The universe is a vast machine of motion, steady and relentless. This isn't just background noise, it's the framework on which everything is built. Motion shapes the structure of galaxies, dictates how stars are born, and governs the lives of planets. It's the heartbeat of the cosmos, constant and precise. In the next part of our journey, we'll follow this invisible rhythm outward to the colossal scale where rotation stops being a local effect and begins to sculpt entire galaxies. When we look up at the night sky, the stars appear scattered randomly like grains of salt across a dark table. But on cosmic scales, their arrangement is anything but random. Rotation, born in the earliest moments of the universe, plays a decisive role in shaping the grand structures we see today. From spinning disks of gas to vast spiral galaxies, The cosmos has used motion as its architect. Every galaxy began as a cloud of matter slowly drawn together by gravity. At first, these clouds were irregular and diffuse, but as they collapsed, even the faintest initial twist amplified. Angular momentum forced the material to flatten just like a spinning lump of clay on a potter's wheel. Over millions of years, that rotating cloud became a galactic disk, its stars and gas locked in a graceful orbit around a common center. This is why so many galaxies, including our own Milky Way, have their familiar spiral shapes. Spiral arms aren't static features like the spokes of a wheel. They're waves of density that move through the galaxy, guiding stars and gas like traffic on a cosmic highway. The rotation of the disk shapes how these arms form, how they persist, and how new stars are born along their edges. Without motion, the galaxy wouldn't be a structured, luminous swirl. It would be a formless haze drifting in the dark. And galaxies don't spin alone. Their rotations are influenced by their neighbours, by mergers, and by the invisible threads of the cosmic web. The structure of the universe, the grand tapestry of matter, is carved by motion on every scale. On the largest scales, galaxies are not scattered randomly through space. They're arranged along colossal filaments of matter called the cosmic web. These filaments are the skeleton of the universe stretching across hundreds of millions of light years. Gravity pulls galaxies toward these threads, but it's rotation that gives them their shape and direction. When a cloud of matter collapses along one of these filaments, the tidal forces gently twist it, giving the forming galaxy a preferred axis of rotation. This subtle alignment has been observed across enormous distances. Galaxies separated by millions of light years often show a statistical preference in how they turn. It's as if the cosmic web isn't just holding them in place, but quietly choreographing their spins. These motions set in the early universe persist to this day, written into the orientation of spiral arms, the tilt of galactic disks, and the flow of clusters through space. Mergers and interactions can reshape these structures, but even then the fundamental momentum isn't lost. When galaxies collide, their rotations blend like colliding whirlpools, forming elliptical giants that still carry the memory of their original motion. These encounters are not random crashes, they are part of a larger flowing pattern. What emerges from all this is a universe that isn't static but sculpted by motion. Every filament cluster and galaxy is part of a shared choreography, a slow and silent turning that began billions of years ago and has never stopped. The deeper we look into this vast structure, the clearer its hidden order becomes. The shape of galaxies, the way they cluster, the paths they trace across the cosmic web, all of it stems from a single elegant principle. Motion doesn't vanish, it organizes. It turns chaos into form. The soft tidal twists of the early universe laid down blueprints that billions of years of gravity have only refined, not erased. Even elliptical galaxies, which seem shapeless at first glance, tell this same story. Most of them are the product of ancient mergers where spinning disks collided and combined their momentum. The result may not be a neat spiral anymore, but their stars still move in coherent, predictable ways. Their orbits remember where the rotation came from. Angular momentum leaves fingerprints everywhere, even where the structure looks blurred to the human eye. And this choreography reaches beyond individual galaxies. Entire clusters rotate slowly around shared centers of mass. Filaments twist as they funnel matter inward. Rotation is not something happening inside the universe. It is something the universe itself is doing. But this dance isn't perfectly balanced. When motion clashes with gravity, the results can be turbulent and unpredictable. To truly understand how spin shapes the cosmos, we must also face its wilder side, where structure bends, collides, and transforms. For all its elegance, cosmic motion is not a perfectly choreographed dance. The same rotation that brings structure to the universe can also unravel it. When galaxies, stars, or entire clusters interact, their motions don't simply align. They collide, twist, and reshape one another in spectacular ways, Rotation, while conserved, can be redistributed, creating both breathtaking order and chaotic transformation. Consider two galaxies drifting toward each other across millions of light years. As their halos overlap, tidal forces begin to stretch and distort them like taffy. Stars are pulled into elongated streams, gas clouds are stirred into turbulent eddies, and spiral arms warp into new shapes. The galaxies may eventually merge, blending their angular momentum into a single, more massive structure. The result is often an elliptical giant, a new galaxy born not from calm formation but from cosmic upheaval. This process is not rare. The universe is full of collisions, and each one is a reminder that rotation is both a stabilizing force and a source of chaos. The same laws that make a galaxy graceful also allow it to be torn apart and remade. Order and disorder are not opposites here. They are partners in a never-ending cycle. In these violent encounters, the universe doesn't break its rules. It rewrites its patterns. The most dramatic displays of cosmic imbalance often appear in the places where gravity and rotation wrestle for control. Around compact objects like neutron stars and black holes, matter doesn't fall quietly inward. It swirls into an accretion disk, a storm of gas and dust moving at a significant fraction of light speed. Within these disks, turbulence reigns. Friction heats the gas to millions of degrees, magnetic fields twist into knots, and the disk itself can warp under its own momentum. From this chaos, jets of plasma erupt into space, powered by the very motion that created the storm. Even on a smaller scale, rotation can lead to instability. In young star systems, the disks that give birth to planets are far from peaceful. Clumps of matter spiral together, their mutual gravity pulling and twisting, forming chaotic streams. Some of these fragments grow into planets, while others are flung into interstellar space. Rotation ensures that nothing is perfectly still. Every imbalance ripples outward, reshaping the system. Collisions amplify this turbulence. When stars pass too close, their gravitational pulls can strip material away or even rip one another apart. When galaxies merge, their spins combine in unpredictable ways, creating intricate tidal tails and chaotic starbursts. Yet even here, beneath the surface of disorder, the same law holds steady. Angular momentum is conserved. The chaos is not a violation of order, it is order rearranged. In the universe, balance is never static, it's constantly negotiated between order and turbulence. Rotation keeps structures stable, but the smallest disturbance can ripple outward, amplifying over cosmic timescales. A slightly uneven mass in a disk can spiral into a storm. A passing star can disrupt orbits forged over billions of years. Even galaxies themselves are vulnerable to these subtle imbalances. Every elegant spiral carries the fingerprints of countless collisions, tidal distortions, and gravitational shoves. Yet through it all, motion endures. Angular momentum doesn't disappear when chaos erupts. It flows, rearranges, and builds something new. The galaxy that forms after a collision isn't a ruined structure. It's a continuation of the same cosmic story written in a different shape. The debris of torn spiral arms becomes new stars. Tidal streams weave into halos. The rhythm of rotation simply changes tempo. This is the dual nature of cosmic motion. The same force that builds order also tears it apart and rebuilds it again. Galaxies spin gracefully not because they have avoided turmoil, but because they've survived it. Their symmetry is forged in fire, shaped by turbulence but never broken by it. If rotation were the only force shaping the cosmos, galaxies would have long since torn themselves apart. Their stars orbit so quickly that by classical physics alone the outer regions should fly off into the void. Yet they don't. Something unseen holds them together, something massive, silent, and everywhere. This invisible glue is what we call dark matter. When astronomers first measured how stars move within galaxies, they expected orbital speeds to decrease at larger distances from the center, much like planets in the solar system. Instead, they discovered something startling. The stars at the edges were moving just as fast as those near the core. This flat rotation curve was impossible to explain with visible matter alone. The gravitational pull of stars, gas and dust simply wasn't enough to keep everything bound. Something else had to be there. Something we couldn't see. Dark matter doesn't emit light. It doesn't absorb it. But it exerts gravity, and that gravity shapes everything. Galaxies are wrapped in enormous halos of this invisible substance, extending far beyond their bright disks. These halos act like anchors, countering the outward pull of rotation and holding galaxies together for billions of years. Without them, spiral arms would unravel, clusters would disperse, and the cosmic web itself would lose its structure. In many ways, the rotation of galaxies is a map of this hidden mass. It reveals not just where stars are, but where the real weight of the universe lies. The evidence for this hidden mass is overwhelming, even if we cannot see it directly. Astronomers have mapped the speeds of stars, measured the motion of gas, and observed the bending of light itself. When light from distant galaxies passes through massive galaxy clusters, it is deflected by their gravity, an effect called gravitational lensing. But the amount of visible matter in these clusters is far too small to explain the bending we see. The missing gravity must come from something else. A vast unseen halo of dark matter. Cosmic simulations add even more weight to this picture. When scientists build virtual universes using only normal matter, galaxies form weakly and quickly fall apart. But when dark matter is included, something remarkable happens. Galaxies form with stable rotation curves, clusters stay bound, and the cosmic web emerges naturally. Dark matter provides the scaffolding on which the visible universe is built. These halos are not passive. They shape how galaxies spin, how they grow, and how they survive collisions. When two galaxies merge, their stars may scatter in tidal streams, but their dark matter halos absorb and redistribute the energy, allowing a new galaxy to stabilize. It's like an invisible frame beneath a sculpture supporting the shape we actually see. Though we may never touch or see dark matter directly, its gravitational fingerprints are everywhere. It is the silent partner in every galactic rotation, the unseen hand that keeps the cosmic dance from flying apart. Dark matter doesn't just keep galaxies intact, it gives the universe its shape. Its gravity forms the deep wells in which normal matter gathers, and its quiet, invisible presence decides how galaxies rotate, where clusters form, and how the cosmic web stretches across space. The visible universe is only the surface layer of something far larger and more intricate. We live inside the shadow of a structure we cannot see. This hidden mass also explains why rotation is so universal. Galaxies can spin at incredible speeds without tearing apart because their halos act as stabilizing anchors. The invisible mass counters the centrifugal force holding stars in orbit even at the farthest edges. And as galaxies interact, their dark halos absorb and distribute angular momentum like shock absorbers in a vast cosmic machine. This is why the large-scale structure of the universe has endured for billions of years. It's humbling to realize that the stars, the planets, even as all the luminous matter we can observe, are just passengers on a greater unseen framework. Dark matter doesn't shine, but it conducts the cosmic orchestra from the shadows, ensuring the dance of galaxies never falls out of rhythm. And this dance is not random. It's a pattern that stretches across unimaginable distances, linking clusters, filaments and galaxies into one interconnected motion. When we step back far enough, the universe begins to reveal its larger pattern. Galaxies are not scattered like leaves in the wind. Their spins and orientations are subtly connected across astonishing distances. This is not coincidence. The same tidal forces that shape the cosmic web also nudged galaxies into alignment, weaving their individual rotations into a shared silent choreography that stretches across the cosmos. Astronomers have detected this cosmic alignment by studying how galaxies spin in relation to the filaments that thread through the universe. Many spiral galaxies rotate along axes that line up with these filaments, as if tracing the flow of invisible rivers of matter. Even galaxies separated by hundreds of millions of light-years show hints of coordination, their spins pointing in similar directions more often than random chance would allow. It's as if the universe has been keeping time since its first moments, and galaxies are still moving to that primordial beat. This phenomenon, called tidal torque theory, suggests that galaxies inherit their angular momentum from the way they form inside the cosmic web. Filaments twist and pull as matter collapses, giving each forming galaxy a spin aligned with its surroundings. Over billions of years, mergers and interactions can blur these alignments, but the original imprint never fully disappears. Beneath the complexity, there is a rhythm. The universe doesn't just spin, it spins together. The idea of galaxies turning in concert across cosmic distances once sounded almost too elegant to be real. But over the past 2 decades, evidence has steadily mounted. Large sky surveys mapping millions of galaxies have revealed patterns that hint at a hidden structure beneath the visible universe. Their spins aren't pointing in random directions. They're arranged in statistically significant alignments, often following the filaments of the cosmic web like dancers following a choreographed path. This subtle order is most clearly seen in younger spiral galaxies whose rotations still reflect their original birth conditions. Elliptical galaxies shaped by ancient collisions show weaker alignment, but still carry faint traces of the same primordial influence. It's as if the universe wrote its first rhythm at the dawn of time, and every galactic spin since then has been a variation on that theme. Gravitational simulations back this up. When scientists model the growth of large-scale structure galaxies forming along filaments, naturally acquire aligned angular momentum, these simulations reproduce the same patterns observed in the real universe, suggesting that the choreography isn't accidental. It's written into the physics of how matter gathers and moves. From filaments to clusters, from clusters to entire superstructures, rotation binds everything into a single cosmic flow. The universe doesn't just expand, it turns. What makes this alignment so profound is its scale. A single galaxy may be vast, stretching over 100,000 light-years, but cosmic filaments span hundreds of millions. To find correlations in spin across such distances means we're not looking at isolated objects. We're witnessing a connected system, a universe that remembers its first motions and carries them forward, like a rhythm echoing through time. These alignments also act as cosmic signposts. By studying the way galaxies are oriented, astronomers can trace the invisible scaffolding of the cosmic web mapping structures that light alone cannot reveal. It's as if rotation itself were drawing the universe's hidden skeleton in space. Every spiral galaxy becomes a compass needle pointing toward the forces that shaped it. This shared choreography is fragile yet persistent. Collisions, mergers, and cosmic turbulence can distort it, but the underlying rhythm is never erased. It lingers in the background like a faint melody beneath the noise, a reminder that the motion we observe today was composed billions of years ago. And this story does not end with galaxies. The same physical principles that govern cosmic spin ripple downward through every layer of reality, from the vastness of intergalactic space to the microscopic world inside atoms, and even into the chemistry that makes life possible. The story of motion doesn't stop at the edges of galaxies. It reaches all the way down to the invisible world of particles, atoms, and molecules, the building blocks of everything, including life. In fact, the same physical principles that govern the rotation of stars also shape the behavior of matter at the smallest scales. Rotation is not just a cosmic phenomenon. It is a universal language written into the structure of reality itself. Every atom in your body carries an ancient rhythm. Electrons do not orbit their nuclei like planets around a star, but they possess an intrinsic form of angular momentum known as quantum spin. This is not a mechanical rotation that can be seen or stopped. It is a fundamental property of matter. Quantum spin determines how particles interact, how they align in magnetic fields, and how atoms bond with one another. Without it, chemistry as we know it would not exist. This microscopic spin gives rise to magnetism. When many electron spins line up, they create magnetic fields strong enough to shape the behavior of entire planets. The compass that points north, the auroras shimmering at Earth's poles, and the shielding that protects our atmosphere from solar wind, all of these trace back to the quantum spins of countless particles aligned in silent precision. The same cosmic rule that keeps galaxies turning also beats inside the smallest fragments of you. At the microscopic level, rotation shapes the chemistry that makes life possible. The way atoms bond and molecules form is not random. It's dictated by how their spins align or oppose each other. Electrons obey strict rules about how they can occupy energy levels, and these rules come directly from their intrinsic angular momentum. The periodic table itself, the grand map of chemical behavior, is built upon patterns set by spin, but the influence of spin doesn't end with atoms. In molecules, a property called chirality, a kind of handedness, emerges from the way atoms arrange themselves in three-dimensional space. This handedness is essential to biology. Amino acids, sugars and DNA all have specific orientations that allow them to fit together like pieces of a puzzle. A molecule with the wrong orientation can behave in a completely different way, even if its chemical formula is identical. And at the heart of this chirality lies a history of how motion shaped the earliest molecular structures. Some scientists suspect that cosmic processes may have influenced this handedness. High-energy radiation, magnetic fields, and polarized light, all products of rotating cosmic systems, could have biased the earliest organic molecules toward a single orientation. If that's true, then the spin of distant stars and galaxies may have quietly tilted the balance that led to the kind of life we know today. In a very real sense, the geometry of life may be an echo of the universe's rotation. Spin doesn't just shape the architecture of molecules, it can influence how life itself begins and functions. Biological systems rely on finely tuned magnetic and chemical interactions, both of which trace back to the behavior of spinning particles. The orientation of molecules determines how they interact with light, how they fold into functional shapes, and how they fit into the machinery of living cells. These tiny angular momenta inherited from the earliest moments of the universe are the silent engines behind everything from DNA replication to the navigation of migratory birds. Life on Earth is also immersed in larger spinning systems. The planet's magnetic field, born from the motion of a molten iron deep below, shields the surface from harmful cosmic radiation. This protection allowed delicate molecules to survive long enough to assemble into something living. Rotation provides both structure and sanctuary, from the tiniest quantum spins that define chemistry to the planetary motions that create habitable environments. This continuity between the microscopic and the cosmic is not a coincidence. It is the same law expressed at different scales. The rhythm that spins galaxies is the same rhythm that turns within every living cell. We are quite literally built from motion. The same motion that shapes stars and galaxies also shields the fragile environments where life can thrive. Earth is a perfect example. Deep beneath our feet, the planet's molten iron core is in constant motion, swirling and turning as the Earth rotates. This movement generates a powerful magnetic field through a process known as the geodynamo. That invisible field stretches far into space, forming a magnetic shield that deflects charged particles streaming from the sun. Without it, the solar wind would strip away our atmosphere, boiling off the oceans and leaving the surface exposed to deadly radiation. This protective shield doesn't just make life on Earth more comfortable, it makes life possible at all. It softens the impact of solar storms, stabilizes the climate, and preserves the delicate balance that allows complex organisms to exist. And it all begins with motion, the rotation of the planet, the churning of its interior, the steady beat of a world that has never stopped turning. But Earth is not alone in this story. Across the solar system, rotation determines which worlds are protected and which are bare. Mars, once warmer and wetter, lost its magnetic field when its core cooled and its rotation weakened. Its atmosphere was slowly stripped away, leaving behind a dry and frozen desert. Jupiter, on the other hand, spins so quickly and has such a powerful magnetic field that it creates vast radiation belts, invisible fortresses encircling the giant planet. Rotation is not only an architect of worlds, it is their guardian. A planet's magnetic shield isn't just a passive shell, it's a dynamic force constantly reshaped by rotation and solar wind. On Earth, this protective field traps charged particles in vast regions called the Van Allen radiation belts, redirecting most of the solar wind around the planet like water flowing around a stone. The magnetic field also guides some particles toward the poles, where they collide with the upper atmosphere and create shimmering curtains of light. The auroras. This spectacular glow is more than a natural wonder. It is visible proof that motion deep within the planet is quietly defending the surface above. Contrast this with Mars. Its smaller size meant its core cooled more quickly, shutting down its geodynamo. Without a strong rotation and molten movement, its magnetic shield faded, leaving the atmosphere exposed to the relentless solar wind. Over millions of years, Mars lost most of its air and water, transforming from a once habitable world into the frozen desert we see today. Meanwhile, Jupiter demonstrates the opposite extreme. Its immense size and rapid rotation generate a magnetic field so strong it dwarfs Earth's. This field carves out an enormous magnetosphere extending millions of kilometers into space. It traps charged particles in powerful radiation belts, creating an invisible fortress around the gas giant. While this environment would be lethal to humans, it's a stunning example of how rotation alone can shape the invisible shield around a world. Rotation doesn't just build these defenses, it sustains them. Without that ceaseless motion, worlds become vulnerable. The presence or absence of rotation can decide whether a world remains alive or falls silent. Magnetic fields born from motion act as planetary guardians, shielding atmospheres from erosion and surfaces from radiation. But these shields are not eternal. When rotation slows or a core cool's protection fades, the world becomes vulnerable to the raw power of its star. This is not speculation. It is written in the contrasting fates of Earth, Mars, and other planets across the solar system. What makes Earth extraordinary is not just its size or composition, but its steady rotation over billions of years. That rotation keeps its core in motion, sustains the geodynamo, and preserves its magnetic shield. It is one of the quiet, often overlooked ingredients of habitability. Without it, the surface of our world might have resembled Mars, stripped, frozen, and silent. And this principle extends beyond Earth. When astronomers search for habitable worlds orbiting distant stars, they don't just look for liquid water or the right temperature. They also consider whether the planet is rotating fast enough to maintain a protective magnetic field. A slow or tidally locked world may lack the shield needed to keep its atmosphere intact. A well-spinning planet, on the other hand, might stand a chance against the fierce radiation of its star. The cosmic rhythm that shapes galaxies also decides the fate of worlds. Motion is not only the engine of creation, it is the shield of survival. Not all motion is equal. A world can spin too slowly and lose its protection, or spin too fast and become a place of violent storms and relentless extreme. Between these two limits lies a delicate rhythm, a tempo just right for stability, for oceans to breathe, for life to take root. This is what makes rotation not just a background feature, but a critical factor in planetary habitability. Earth's rotation strikes this balance beautifully. A single day lasts 24 hours, long enough for heat to distribute between day and night, yet not so long that one side bakes while the other freezes. This steady turning drives wind and ocean currents, mixing the planet's atmosphere and moderating its climate. Without it, the contrast between day and night would be brutal. A slow-spinning Earth would see its oceans boil on one side and freeze on the other. But rotation is also powerful in excess. Jupiter spins so rapidly that a single day lasts just 10 hours. This speed fuels ferocious jet streams and colossal storms, including the Great Red Spot, a hurricane larger than Earth that has raged for centuries. For a habitable planet, too much spin can create chaos. Wild winds, violent climate patterns, and unstable seasons. Somewhere between these extremes lies the Goldilocks tempo, where rotation nurtures rather than destroys. A rhythm slow enough for gentle cycles, fast enough to protect and stable enough to last for billions of years. The rhythm of a planet's rotation sets the stage for everything that happens on its surface, climate, atmosphere. Even the daily behavior of living organisms are synchronized with this silent beat. On Earth, the 24-hour day is long enough for temperatures to even out between day and night, creating a stable and predictable environment where ecosystems can flourish. Winds circulate warmth, ocean currents distribute energy, and the result is a world with dynamic but livable weather. A slower spin would throw this balance into turmoil. Imagine a planet where a single day lasts months. One hemisphere would face the star for weeks, baking under constant sunlight, while the other froze in unending night. The atmosphere would convect violently between the two, creating storms of unimaginable scale. Such worlds could exist. In fact, many planets orbiting red dwarf stars are tidally locked forever, showing one face to their star. These worlds may have narrow habitable zones along their twilight edges, but their climates are far less forgiving. On the other hand, a faster rotation can push weather to extremes. Rapidly spinning planets develop stronger Coriolis forces, invisible effects that curve moving air and water. This leads to fierce jet streams, towering cyclones, and unpredictable climates. Jupiter is a prime example. Its breakneck rotation fuels jet streams that wrap around the planet, sustaining storms that have lasted for centuries. A similar effect on a terrestrial world would create a climate too unstable for a complex life to thrive. This is why the speed of rotation isn't a trivial detail. It is a climate engine setting the tempo for wind, water, and life. Rotation does more than regulate a planet's climate. It shapes the rhythm of time itself for any life that emerges. The length of a day becomes the heartbeat of ecosystems. Plants open and close their leaves in tune with sunlight. Animals hunt, migrate, and sleep according to the rising and setting of the star they orbit. Even the cells in our bodies follow circadian cycles, internal clocks that evolve to match the Earth's steady 24-hour turn. Change that tempo and life would have to rewrite its rules. This delicate balance is rare. If Earth spun just a bit faster, our days would be shorter, winds stronger, and weather far more volatile. If it spun more slowly, nights would lengthen, temperatures would swing wildly, and ecosystems might collapse. Over billions of years, this steady tempo has acted like a metronome, keeping the surface environment stable enough for life to evolve, adapt, and flourish. And it's not just about today. Earth's rotation has been gradually slowing down over time due to tidal interactions with the Moon. In the distant past, days were shorter, yet the planet has remained within a stable range, a testament to how rotation, gravity, and orbital mechanics work together to keep Earth's climate in balance. Rotation is not only the architect of worlds and climates, it is the keeper of time, the clock by which life itself learns to exist. Before clocks, before calendars, before humanity even existed, there was rotation. The turning of worlds and the movement of stars were the first keepers of time. Every sunrise and sunset, every passing season, every heartbeat of cosmic rhythm comes from the simple fact that nothing in the universe stands still. Time as we experience it is measured not by an external standard but by motion itself. On Earth, one rotation defines a day, one orbit defines a year. These cycles gave rise to our sense of time long before we had language to describe it. Ancient civilizations watched the sky, marking the movement of the sun, the stars, and the moon. Their calendars, rituals, and stories were all woven from the regularity of cosmic spin. To them, time was not an abstract concept. It was written in the heavens. But rotation doesn't just set human timekeeping. It sets the physical stage for how time is experienced. As a planet spins, it divides its world into cycles of light and darkness. These cycles shape everything from climate to the behavior of living things. Even the slow drift of continents and the changing tilt of Earth's axis are part of this great temporal engine. Every second we live is measured against the turning of our world. Time is not separate from motion. It is motion transformed into rhythm. Our understanding of time is inseparable from the way the universe moves. Every clock we build is ultimately a reflection of some natural rhythm. The turning of the Earth, the vibration of atoms, the steady ticking of pulses across the cosmos. Long before we could build precise instruments, the heavens themselves kept perfect time. The rising and setting of stars, the phases of the moon, and the shifting of the seasons gave our ancestors their first calendars. Even today, our most advanced systems still rely on cosmic motion. The length of a second is defined using atomic vibrations, but our days and years remain tied to the rotation of our planet and its orbit around the Sun. Space agencies time rocket launches down to the second using these cycles. Farmer sailors and scientists all live by a schedule set in motion billions of years ago when the Earth first began to turn. And on an even grander scale, cosmic time is marked by the movements of galaxies and stars. Pulsars rapidly rotating neutron stars emit beams of radiation with such perfect regularity that they rival atomic clocks. Astronomers use these pulses to measure distances, detect gravitational waves, and study the curvature of space-time itself. In a universe where everything spins, time is simply the record of that endless motion. Rotation doesn't just give us time to measure, it gives us a reference, a cosmic beat that keeps everything in sync. When we strip away our calendars and clocks, what remains is something far older, the universe's own heartbeat. Rotation is the original metronome. It keeps time not in numbers or units, but in the steady turning of worlds, the swirling of galaxies and the quiet rhythm of stars. It is this ceaseless movement that allowed civilizations to measure days and nights, to plant and harvest, to build everything we call history. But beyond human perception, rotation is time made visible. Every turn of the Earth moves us forward. Every orbit of a star around a galactic core writes another line in the cosmic timeline. Even the rotation of black holes carries time's imprint, slowing it near their horizons, bending it in ways that defy intuition. Time is not some distant force acting on the universe. It is born from the universe's own motion. And when we look upward across billions of light years, we're not just seeing distant galaxies. We are seeing different moments in the great clock of the cosmos, each turn frozen in light that has travelled for eons to reach us. To observe the universe is to read its time. We live inside a clock that never needed to be built. From the moment the universe was born, it has never stopped moving. Rotation is not a temporary feature or a passing phase. It is the thread that has stitched reality together from the beginning. Long before stars burned or galaxies formed, faint quantum ripples twisted through the newborn cosmos. Those ripples were stretched by inflation, amplified by gravity, and written into the fabric of space itself. Every orbit, every spiral, every turning world is an echo of that first silent motion. We can see its fingerprints everywhere. Galaxies spinning in graceful disks, planets turning steadily on their axes, atoms holding their intrinsic quantum spins, black holes twisting space-time around them like invisible whirlpools. Even the cosmic web spanning billions of light years carries the faint alignment of motion seeded at the dawn of time. Motion is the one thing the universe has never lost. It doesn't matter how matter changes, how stars are born or die, or how galaxies collide and merge, the spin persists. It shifts shape flows between scales, but it never disappears. It is conserved, protected, and carried forward like an unbroken melody across cosmic history. We do not live in a still universe. We live in a universe that turns. This motion is not confined to the past. Even as stars burn out and galaxies drift apart, rotation will endure. In the distant future, long after our sun has faded and the Milky Way has merged with Andromeda Galaxy, the cosmic web will continue to twist and flow. Stars will still orbit galactic cores. Black holes will still whirl space-time around them. Neutron stars will still tick like perfect clocks. Spin is not something that fades with age, it is as timeless as the universe itself. As the cosmos expands, its structures will grow quieter, colder, more isolated, yet motion will not stop. Even in a thin, dark, almost empty universe, the last black holes will carry angular momentum like ancient archives of the Big Bang's earliest moments. Their spin will curve space-time and radiate energy slowly through Hawking radiation, whispering the final rhythm of creation. And when even those black holes evaporate into the deep darkness, the laws that made them spin will remain unchanged. The conservation of angular momentum, that elegant, unbreakable rule, will still be written into the geometry of reality, even if there is little left to turn. The universe is not heading towards stillness. It is heading towards silence, but even in that silence, the memory of motion will live on. In the end, everything returns to the same truth. The stars that light the night sky, the planets beneath our feet, the atoms in our bodies, all are passengers in a universe that has never stood still. Rotation is the silent architect, the invisible conductor, the ancient rhythm beneath all things. It has no beginning and no end, only transformations. From quantum ripples to galaxies, from galaxies to worlds, from worlds to life. When we look at the slow turning of Earth, we are witnessing the same principle that spins distant black holes. When we feel the passage of a single day, we are moving in step with a pattern written at the birth of time. And when we gaze into the night sky, we're not just looking outward, we're looking backward, reading the record of motion carved into the cosmos itself. The universe does not need to be pushed. It turns because it always has. It carries its past in every orbit, every spin, every swirling storm of matter and light. This eternal motion is the heartbeat of creation, a rhythm that has guided everything that exists and everything that will ever be. We are not separate from it. We are part of the spin. In the beginning, motion was nothing more than a whisper. It had no stars to anchor it, no worlds to trace its curves, no orbits to hold its shape. But as the young universe expanded and cooled, those faint movements began to gather weight. Invisible ripples stretched into grand arcs, pulling loose matter together. What began as scattered streams of particles slowly coalesced into clouds, and those clouds began to turn. In those ancient motions lay the seeds of everything that would follow. Tiny asymmetries. The smallest imperfections in the early cosmos were amplified as space itself expanded. Where matter gathered, gravity tightened its grip. Where motion curved structure emerged, swirls of gas and dust spiraled inward, tracing invisible pathways that would soon become the skeleton of galaxies. In this silent unfolding ballet, the universe crossed a threshold. Movement was no longer just a property of reality, it became the blueprint of reality. Every orbit, every pattern, every cosmic cycle to come began as this simple act. Motion turning into structure. At its core, this transformation follows a simple rule. Gravity pulls and momentum resists. When matter begins to fall inward, it rarely collapses straight down. Even the smallest sideways motion creates a curve, and that curve grows. As the collapsing cloud tightens, its spin increases, conserving angular momentum. What was once a drifting mist becomes a swirling disk. Gravity sculpts the motion, and motion sculpts the structure. This is how the first cosmic shapes were born. Vast hydrogen clouds, light years across, began to flatten and twist under their own gravity. Within them, pockets grew denser, their rotations sharpening like a skater pulling in their arms. These whirling structures were the cradles of the first stars that would ignite, fuse hydrogen, and light up the darkness. The same physical laws that turn a falling leaf into a spiral also turn galaxies into majestic spinning wheels. And this process didn't just happen once. It repeated scale after scale, from tiny eddies in primordial gas to colossal galactic disks. Rotation became the architect and gravity, its silent partner, building the universe not through stillness but through motion. As the universe aged, this dance repeated endlessly, layering motion upon motion. What began as drifting particles grew into swirling nebulae. Those nebulae folded into stars gathered into galaxies, and galaxies settled into their vast cosmic highways. Every structure we see in the night sky, from the curve of a spiral arm to the graceful ring of a planet's orbit, can trace its lineage back to those first turning clouds. It is motion, not stillness, that gives shape to the cosmos. Even today, billions of years later, the universe still remembers how it began. The same laws that shaped the first star-forming disks continue to guide the movements of entire clusters of galaxies. The same patterns ripple outward like echoes across space and time. What seems like chaos at first glance is in fact a choreography written in gravity and motion, and from this great turning comes something even more profound. When matter follows these paths long enough, motion ceases to be just rotation. It becomes orbits, stable, elegant, enduring paths that carry the universe forward in time. There is a moment when chaos finds rhythm. A swirling cloud, once wild and unpredictable, tightens and steadies its motion. Matter stops falling inward in straight lines and begins to loop gracefully around a common center. This is the birth of orbits, the moment when motion stops being a storm and becomes a pattern. Orbits are nature's way of creating stability out of turbulence. A grain of dust, a rock, a planet, or an entire star can follow a curved path around something larger without ever touching it. No walls hold them in place, no ropes pull them back. Instead, gravity bends their motion into elegant arcs, and momentum keeps them from falling. It's a perfect balance between two forces, one pulling inward, the other carrying forward. This balance allows the universe to build lasting structures. Worlds can circle stars for billions of years. Moons can dance around their planets. Stars can whirl around galactic cores. Every orbit is a silent agreement between gravity and motion, a harmony so stable that entire histories can unfold upon it. Every orbit begins as a negotiation between falling and moving. Gravity pulls matter inward, bending its trajectory toward the center of mass, but momentum resists carrying it forward tangential to the pull. When these two forces find equilibrium, a closed path emerges, the curved line of an orbit. This is why a planet does not plunge into its star, why a moon does not spiral endlessly away, why entire galaxies can rotate without collapsing in on themselves. It doesn't take a perfect circle to make this work. Most orbits are ellipses, graceful ovals where a body speeds up as it draws closer to its star and slows down as it drifts away. This natural ebb and flow is part of what makes the orbital dance so stable. As long as no outside force interferes too strongly, the rhythm can last for billions of years. The Earth has traced its path around the Sun for 4.5 billion years without missing a beat. This balance is the foundation of cosmic architecture. It allows structures to endure while everything within them is in constant motion. Stars circle the hearts of galaxies, galaxies themselves drift through the cosmic web, and even clusters of galaxies orbit shared centers of gravity. Orbits are not the absence of change, they are permanent motions sculpted into elegant paths. Over cosmic time, these loops became the backbone of structure. Stars found their places in galactic arms, circling their centers in vast unbroken cycles. Entire planetary systems settled into steady rhythms where each world traces its invisible lane around its star like dancers on a choreographed stage. And even galaxies themselves are caught in greater orbital flows, drifting through the cosmic web along paths defined long before they formed. This transformation is extraordinary. A chaotic cloud that once moved in every direction becomes a structured system where each body follows a predictable path. These paths don't just contain matter, they give the universe its stability. Through orbits, gravity and motion stop pulling against each other and start working together, weaving order out of a restless cosmos. From these orbits come tides, seasons, cycles, and entire histories. They are the quiet stage upon which the drama of the universe unfolds. And when these motions begin to align, they create something even more intricate. Resonance, a deeper layer of cosmic harmony. When orbits align, the universe begins to sing. What was once a collection of separate motions starts to fall into rhythm, a pattern that repeats itself like the steady beat of a drum. Moons, planets, and stars settle into orbital resonances, subtle gravitational agreements that allow multiple bodies to move together without tearing each other apart. This is where motion stops being just structure and becomes harmony. You can see this harmony in the quiet precision of planetary systems. One world circles its star and another follows at just the right distance, so their gravitational pulls never collide but instead dance in step. Their periods become simple ratios, 2 turns for 1, 4 for 2. A perfect cosmic rhythm that can last for billions of years. These resonances are not accidents. They are the natural outcome of motion refining itself over deep time. This is why many systems across the cosmos display a kind of mathematical elegance. Planets, moons, and rings fall into ratios and patterns like instruments in a vast orchestra playing the same hidden song. Harmony is not a human invention, it is a property of motion itself. Orbital resonance happens when 2 or more bodies circle a central object in synchronized rhythms. Their gravitational pulls gently tug on each other, not chaotically, but in a way that reinforces stability. Instead of collisions, they create repeating patterns. A classic example lies around Jupiter, where 3 of its largest moons, Io, Europa, and Ganymede, follow a 1, 2, 4 resonance. For every 1 orbit of Ganymede, Europa makes 2 and Io makes 4. It's a perfectly balanced gravitational rhythm that has lasted for billions of years. These resonances aren't rare curiosities, they are everywhere. They stabilize planetary systems, control the spacing of moons, and shape the rings of giant planets. Even the delicate patterns in Saturn's rings are sculpted by tiny moons, whose gravitational influence sets the particles into rhythmic oscillations. What might look like stillness from afar is actually a finely tuned dance. The beauty of resonance is its resilience. Once these ratios lock in, they can persist for astonishing lengths of time. Even small disturbances tend to nudge the system back toward its original beat, as if gravity itself prefers a well-rehearsed choreography. Resonance is motion made elegant, not chaos, but cosmic music. This synchronized rhythm doesn't stop at moons and planets. It extends into the great architecture of the cosmos. Stars orbit within galaxies in vast streams that rarely collide. Whole clusters of stars move in gently layered flows following resonant patterns set long ago. Even galaxies themselves, bound together in clusters, trace enormous orbital paths around shared gravitational wells, falling into subtle alignments, like dancers spread across a stage too vast to see. These hidden resonances act like the framework of a great machine. They bring order where pure gravity alone might cause chaos. Over billions of years, unstable motions fade, collisions settle, and what remains are the stable rhythms that can last longer than stars themselves. The universe doesn't just contain harmony, it naturally evolves toward it. And from these rhythms, something remarkable emerges. Cycles, seasons, time itself. When orbits fall into predictable patterns, they become the clocks of the cosmos. Worlds measure their days and years not with devices but by the motion of the heavens above. This is the beginning of celestial timekeeping, the foundation of the clockwork sky. Long before humanity invented clocks, the sky already kept time. The steady turning of the Earth, the looping of the moon, and the orbit of our world around the sun formed a grand celestial mechanism, a cosmic clock whose gears are orbits, whose hands are stars. Every sunrise and sunset, every shifting season, every pattern in the heavens traces back to orbital motion. The sky does not just shine, it ticks. Ancient observers didn't need technology to sense this rhythm. They watched the same stars rise at the same time. Each year saw shadows grow longer or shorter as the planet moved along its orbit, and felt the cycle of light and warmth repeat with flawless precision. From these motions came calendars, navigation, agriculture, entire civilizations built upon the silent turning of the heavens. The clockwork of the sky is not the work of human hands. It was forged in the earliest days of the solar system when gravity shaped the Earth's orbit and set the moon in motion. The ticking of this cosmic clock began long before we could name it, and it will continue long after we are gone. Every measure of time we use is born from an orbit. A single rotation of Earth defines the day, the rhythm of light and darkness that governs every creature's life. The moon's orbit defines the month, marked by its phases waxing and waning in the sky, and one long journey around the sun gives us the year, the great cycle that brings seasons, tides, and renewal. What we call time is really the echo of motion, the repetition of cosmic paths written into the structure of space. These cycles are so precise that they became the foundation of all human order. Farmers planted by them, sailors navigated with them, priests and astronomers carved them into stone calendars and temples that aligned perfectly with the rising sun or the returning constellations. Even now, our digital clocks ultimately trace back to the same origin, the Earth turning beneath us, the moon, looping above the planets, flowing through their orbits like gears in a vast machine. And yet nothing in this clockwork is truly rigid. The rotation of Earth slows ever so slightly as the moon drifts away, lengthening our days by a fraction of a second every century. Seasons shift over tens of thousands of years as our orbit tilts and wobbles. The cosmic clock does not break, but it breathes a living rhythm that evolves as the universe itself does. When we look at the stars, we're not just seeing distant suns, we're reading time. Every cycle in the heavens is a marker, a beat in the grand metronome of the universe. The tilt of Earth defines seasons. The orbit of the moon shapes tides. The motion of the planets traces silent loops across the sky. All of these together weave a tapestry of time that existed long before humanity could measure it, and will continue long after our clocks have stopped ticking. This is what makes orbital motion so extraordinary. It doesn't simply mark time, it creates it. Without rotation and revolution, there would be no day, no month, no year. Life itself, from migration patterns to flowering seasons, has evolved to move in step with these rhythms. Even our biology is tuned to the turning of the Earth, our internal clocks beating in time with the sky. Time is not a separate force watching over the cosmos. It's written into the motion of the heavens. And through that motion, the universe doesn't just exist, it stays organized. Orbits hold systems together, define stability, and allow time to flow with breathtaking precision. Orbits are more than beautiful curves in space. They are the silent architects of stability. Every star system, every galaxy, every spinning world is held together by a delicate balance between motion and gravity. If gravity alone ruled, everything would collapse into a single point. If motion alone dominated, everything would fly apart into the void. But orbits sit in the perfect space between, creating long-lived structures where complexity can thrive. A planet tracing a steady path around its star does more than move, it anchors the system. Its predictable position allows other bodies to settle into their own orbits, forming a web of mutual balance. Moons fall into resonance with their planets. Planets align with their stars, and stars dance around galactic centers. This layering of orbital paths creates a hierarchy, a cosmic framework where everything has its place and rhythm. This quiet order is why the universe doesn't dissolve into chaos. Orbits let things endure. They allow stars to shine steadily for billions of years, planets to hold their climates stable, and galaxies to keep their spiral arms intact. They are the invisible structure beneath all cosmic architecture. Stability is not an accident, it's the result of precise physical laws at work. When a body moves in orbit, its forward momentum is perfectly balanced by the inward pull of gravity. If it moves too slowly, it falls inward. Too quickly, it escapes. But at just the right speed, it enters a stable path that can last billions of years. This equilibrium is why the Earth continues to trace its orbit around the Sun year after year, never spiraling away and never plunging inward. The same principle shapes entire systems. In multiple star configurations such as binary or trinary systems, orbital stability determines whether planets can survive or be flung into interstellar space. Around Jupiter, dozens of moons orbit in carefully balanced lanes, their paths shaped both by the planet's gravity and by one another's subtle tugs. Even in densely packed regions like star clusters, orbits can find equilibrium over immense spans of time, creating complex yet remarkably stable arrangements. And it doesn't stop there. At galactic scales, billions of stars move in vast synchronized flows around a common center. These orbits don't collide chaotically, they cooperate. Gravity holds the system together, but it is motion that prevents collapse. The universe is not balanced on the edge of destruction. It is held steady by the perfection of orbital dynamics. Across every scale of the cosmos, orbits act like a quiet engine of organization. In solar systems, they allow planets and moons to keep their places without constant collisions. In galaxies, they guide stars into streams and arms, arranging billions of suns into vast harmonious patterns. And in galaxy clusters, they weave colossal paths that keep entire cosmic cities from falling apart. This isn't chaos. It's the universe choosing structure through motion. Even when systems evolve, when stars die, when planets shift, when galaxies collide, orbits remain the underlying language that reshapes the order, rather than destroying it. They stretch, they warp, they merge, but the principle of balance endures. It's this resilience that allows the cosmos to remain structured over billions of years long after individual stars have burned out. And from this foundation of stability emerges something even more intricate: resonance. When orbits don't just coexist but interlock, they form rhythms that echo through entire systems. This is where structure becomes harmony, and the quiet balance of orbits transforms into celestial music. When multiple orbits fall into rhythm, the universe stops merely spinning, it begins to sing. Celestial resonance is one of the most elegant consequences of motion. Bodies circling a shared center settle into repeating ratios like instruments locked in harmony. Their gravitational pulls don't tear each other apart. Instead, they stabilize one another, reinforcing a rhythm that can last for billions of years. This harmony isn't forced, it emerges naturally. As planets, moons, or ring particles move through space, their mutual gravity adjusts their speeds and distances until their orbits fall into stable patterns. One body might complete 2 revolutions, while another finishes 1 or 4 to 2 or any ratio in between. Once this balance is found, it locks in like the tension of a perfectly tuned string. The result is astonishing. Systems that might otherwise dissolve into chaos instead become orchestrated dances. These rhythms ripple through planetary systems, star clusters, and even galactic structures. Resonance is how the universe keeps its music playing. Resonance begins with subtle gravitational conversations. As 2 or more bodies orbit a common center, their gravity tugs gently at one another. If their periods are in the right ratios, these tugs occur at the same point in each orbit, reinforcing rather than disrupting the motion. Over time, these rhythmic nudges bring the system into perfect alignment. Instead of chaos, the result is lockstep motion, a stable relationship that can endure across cosmic ages. One of the clearest examples lies around Jupiter, where 3 of its major moons, Io, Europa, and Ganymede, form a one. Of resonance. For every orbit of Ganymede, Europa completes 2 and Io completes 4. This elegant ratio prevents the moons from colliding, keeps their orbits stable, and even drives Io's volcanic activity through gravitational flexing. It is a perfect example of motion turning into structure and structure sustaining motion. These patterns aren't limited to moons. Rings around Saturn are carved by resonance with tiny shepherd moons, maintaining crisp edges and delicate waves in the icy debris. Entire planetary systems show similar signatures. worlds lock together in ratios that reveal a long history of gravitational choreography. Resonance isn't rare. It's the universe's way of keeping time. What makes resonance remarkable is how it scales upward. The same principle that locks moons around a planet can shape entire galaxies. When stars' gas and dark matter move together in synchronized rhythms, they create self-sustaining structures that can survive for billions of years. These cosmic harmonies don't just preserve order, they build it. Inside spiral galaxies, waves of density sweep through the disk like the repeating beat of a drum. Stars and gas clouds pass through these waves, bunching together and igniting new bursts of star formation. Even the grand spiral arms of our own galaxy aren't fixed objects. They are the result of resonant patterns between rotation and gravity, maintained by the constant motion of billions of stars. It's a galaxy-scale waltz, slow and graceful yet precise. And it doesn't stop there. Clusters of galaxies also fall into patterns orbiting shared centers of mass in colossal loops. The cosmic web itself carries hints of subtle alignment, a faint resonance stretched across hundreds of millions of light years. What began as a gravitational conversation between two small bodies becomes a chorus that reaches to the edge of the universe. From a distance, spiral galaxies look like frozen whirlpools of light. Their luminous arms curl outward in elegant arcs, giving the illusion of stillness. But beneath that serene surface lies a storm of motion. Every spiral is carved and sustained by the orbits of billions of stars moving in harmony, bound together by gravity yet carried forward by their own momentum. These vast structures are not static, they're alive with rotation. In a spiral galaxy, stars don't move with the arms like paint on a spinning wheel. Instead, the arms are waves of density sweeping through the disk. As stars and clouds of gas pass through these waves, they slow down, slightly pile up, and then spread out again. This gathering of matter creates the glowing spiral pattern, a kind of cosmic traffic jam that moves more slowly than the stars themselves. It's not the stars that are fixed, it's the pattern that persists. This delicate balance of orbital motion and gravitational rhythm is why spiral galaxies can hold their shape for billions of years. Their arms aren't rigid structures, but living patterns, spirals of resonance written across hundreds of thousands of light years. The graceful spirals of galaxies are not accidents. They're the natural outcome of gravity and motion finding long-term equilibrium on a cosmic scale. Each star in a galaxy orbits the galactic center, at speeds determined by the mass enclosed within its orbit. Near the center, stars move faster. Farther out, they slow down, but not as much as classical physics once predicted. Instead of unraveling, the disk maintains its structure and the spiral arms endure. Something unseen, the vast halo of dark matter holds the galaxy together, anchoring its spin. These spiral arms form what astronomers call density waves. They travel through the galactic disk like slow-moving ripples on water, and as stars and gas flow through them, matter gathers and lights up in bursts of star formation. This creates the illusion of fixed arms, but in truth the stars are always moving on their own paths. The pattern remains even as the players change. This mechanism is astonishingly stable. A spiral galaxy can keep its shape for billions of years without solid edges or fixed structures. It is a choreography held together not by walls or strings, but by the invisible agreement between gravity, orbital motion, and time. These spirals are more than just beautiful shapes, they are the fingerprints of the universe's vast motion. Each arm traces the history of stellar orbits, density waves and gravitational resonance unfolding over billions of years. When galaxies are born from collapsing clouds, they don't settle into rigid structures. Instead, their stars begin to circle, their gas flows inward, and the spiral emerges naturally as motion organizes itself into pattern. But galaxies don't exist in isolation. They orbit within clusters influenced by the pull of neighboring giants. Their arms are stretched, twisted, and sometimes merged, yet the underlying rotation endures. Even when galaxies collide, their stars rarely crash directly. Instead, their orbits are reshaped into new patterns, giving rise to magnificent tidal streams and warped disks. Motion persists and new structures grow from the remnants of the old. This is the beauty of galactic spirals. They're not fixed monuments, but living records of cosmic motion. And as galaxies themselves fall into larger flows orbiting within clusters, and the cosmic web, these patterns are woven into something even grander. A universe of orbits moving together on a scale almost too vast to imagine. If we could step back far enough to see the entire cosmos at once, we wouldn't see a static picture. We'd see motion and intricate choreography stretching across billions of light years. Galaxies don't float in stillness. They orbit, drifting through gravitational landscapes shaped by clusters, filaments, and invisible halos of dark matter. The universe isn't frozen, it's flowing. Every galaxy, no matter how massive, moves under the influence of structures larger than itself. Spiral giants orbit within clusters. Clusters orbit within superclusters, and all of it is threaded along the cosmic web, an immense network of filaments and voids that spans the observable universe. These motions are slow compared to the turning of stars or planets, but their scale is staggering. Colossal arcs traced over billions of years. It's easy to think of orbits as something local, a planet around a star around a galactic core. But on the larger stage, these same principles shape everything. Gravity reaches across the void, linking distant islands of light into a single interconnected dance. The universe isn't just expanding, it is turning on every scale we can measure. At the larger scales, gravity becomes the sculptor of cosmic geography. Clusters of galaxies bound together in enormous associations orbit shared centers of mass, just as planets orbit stars. Their paths are slow measured not in years but in billions of years, yet the same principles apply. Each orbit is born from the balance between the pull of gravity and the inertia of motion. Even at these unfathomable distances, the universe obeys the same quiet laws. Superclusters, vast continent-sized structures of galaxies, are themselves shaped by this flow. Along the filaments of the cosmic web, galaxies fall inward spiral around gravitational wells and slowly merge over cosmic time. These invisible rivers of motion direct the evolution of entire regions of the cosmos. The orbits here are so enormous that a single circuit can take longer than the age of the Earth. And then there is dark matter, the hidden hand behind the structure. Its vast halos envelop galaxies and clusters, anchoring their movement and preventing them from flying apart. Without it, the cosmic web would fray, the filaments would thin, and the orbits would unravel. Dark matter doesn't glow, but it holds the universe together, keeping the great cosmic dance from scattering into the void. The deeper we look, the more the universe reveals a single unbroken theme. Motion binds it all together. The same principles that hold a moon around a planet and a star in its galactic path are echoed in the way entire clusters of galaxies orbit through space. From the smallest scales to the largest, everything follows the same choreography. A cosmic hierarchy of orbits nested within orbits, each layer shaped by the one above it. What makes this grand structure extraordinary is its consistency. The mathematics describing a spacecraft circling Earth can in essence describe a galaxy orbiting the gravitational center of a cluster. The equations are the same, only the scales change. And through this elegant repetition, the universe maintains its shape across time, resisting collapse while avoiding chaos. It doesn't need new rules for each scale. It just needs gravity, motion, and time. This harmony creates a kind of cosmic architecture. Within these vast orbital frameworks, stars are born, galaxies evolve, and entire histories unfold. And when the scale shrinks from superclusters down to individual worlds, this same orbital order takes on its most intimate role, shaping the climates, rhythms, and destinies of planets. Every world is defined not just by what it is, but by how it moves. A planet's orbit determines the amount of light and heat it receives, the length of its seasons, and even whether its surface can host life. The invisible path a world traces through space is as important as its oceans, atmosphere, or geology. Without stable orbits, the calm rhythms that sustain life would unravel into chaos. Take Earth. Its nearly circular path around the Sun delivers a steady stream of energy, creating mild, predictable seasons. This regularity has allowed ecosystems to flourish, evolving in rhythm with the turning of the sky. A small shift in orbital distance eccentricity or tilt could plunge the world into extremes, blistering heat, endless winters, or erratic cycles too harsh for complex life to endure. This is why orbits are not just a celestial curiosity, they are the quiet architects of habitability. A planet's place and path through space dictate its destiny. Some worlds are too close to their stars, scorched by relentless radiation. Others wander too far, frozen in eternal night. But between these extremes lies the fragile balance where worlds can breathe, oceans can flow, and life can thrive. A planet's orbit is more than a line, it's a climate engine. Its shape, distance from the star, and orientation determine the rise and fall of temperatures, the strength of winds and tides, the rhythm of seasons. A perfectly circular orbit provides consistent energy, fostering stable environments, but stretch that orbit into an ellipse, and the world swings between extremes, scorching summers and freezing winters that can reshape entire ecosystems. The tilt of a planet's axis combined with its orbital path carves out seasonal patterns. Earth's tilt gives us changing sunlight, shifting winds, and migrating storms. Remove that tilt and seasons vanish. Increase it too much and the world becomes a land of violent climate swings. Even the timing of a planet's spin relative to its orbit can lock it into strange fates. Like worlds where one side forever faces the star while the other sleeps in darkness. And then there's the matter of orbital stability. A slight gravitational nudge from a passing star or a neighbouring planet can stretch or shrink an orbit, disrupting climates over thousands of years. These subtle shifts have shaped Earth's own history, triggering ice ages and warm periods. Life, it turns out, doesn't just live on a planet, it lives inside an orbit. Throughout the cosmos, orbits sculpt the fates of planets. In our own system, Mercury races around the Sun in a highly eccentric path, baking and freezing in turn as it moves between extremes of distance. Mars, with its more elongated orbit and thin atmosphere, endures vast temperature swings that leave its surface locked in cycles of frost and thaw. Meanwhile, Earth's near-perfect circular path allows for gentle, steady climates, a rarity that helped life flourish. Beyond our solar system, the variety is even more dramatic. Astronomers have found hot Jupiters, giant worlds locked in tight orbits so close to their stars that their skies blaze with searing heat. Others follow wild, stretched-out paths that plunge them into long winters before brief, intense summers. Some planets orbit two stars at once, living under skies of double sunsets, while others are tidally locked with one hemisphere eternally scorched and the other frozen in darkness. All of this is written in their orbits. A single curve through space decides whether a world becomes a furnace, an ice ball, or a cradle for life. Orbits don't just guide motion, they shape destiny. And when those paths stray too far from perfect balance, they reveal another face of the universe. The power and fragility of eccentric paths. Not every orbit is calm and circular. Many worlds travel through space on long-stretched ellipses paths that bring them scorching close to their stars before casting them back into the cold. These eccentric orbits are a reminder that the cosmos is not built for comfort. It is dynamic, restless, and full of unpredictable turns. For the planets caught in these trajectories, the difference between seasons is not subtle. It is a matter of survival. As a world swings inward on its elliptical path, its star floods it with energy, driving fierce heat, violent winds, and storms that can reshape landscapes. When it drifts outward again, that same world can freeze its atmosphere, collapsing in the chill. Life, if it exists, must adapt to rhythms far harsher than anything Earth has ever known. A single orbit becomes a journey through extremes. These unstable paths are not rare exceptions. They are common across the galaxy, shaped by gravitational encounters, planetary migrations, or the lingering scars of cosmic collisions. Eccentricity is not a flaw. It's the universe showing its untamed side where order bends but doesn't break. An eccentric orbit begins with a disturbance, a gravitational whisper that becomes a cosmic push. When a planet forms, its path may start nearly circular, but over millions of years the steady pull of neighbouring worlds, the passage of rogue stars, or even the slow tug of a massive disk of dust can stretch that orbit into an ellipse. The result is imbalance, a journey where distance, sunlight and time twist into cycles of instability. These elongated paths create dramatic consequences. Temperatures can swing by hundreds of degrees between perihelion and aphelion, the closest and farthest points from the star. Atmospheres expand and contract. Like living lungs, oceans may freeze and thaw, and storms can rage with planet-wide force. Even the shape of a world's magnetic field can fluctuate as it moves through varying radiation zones. Over time, these stresses can strip away atmospheres, shift climates, or ignite volcanic activity deep within the crust. But eccentricity isn't only destructive, it's also creative. The shifting tides and fluctuating energy can drive geological renewal, stirring planetary interiors and influencing evolution. On some worlds, the instability itself may keep them geologically alive long after their cores should have gone cold. In the cosmic balance, even chaos has purpose. Eccentricity doesn't exist in isolation. When one orbit stretches, it can set off a chain reaction. Neighbouring planets feel the tug moons shift their paths, and the entire system begins to breathe with a new, more unpredictable rhythm. Over time, these interactions can reshape the layout of a planetary system, pulling some worlds into new configurations, while flinging others out into interstellar space. Eccentric orbits are catalysts, they rewrite cosmic architecture. This same phenomenon can be seen on grander scales. When galaxies interact, their stars don't collide directly, but their orbits warp and stretch like soft metal under pressure. Tidal forces twist their shapes, fling streams of stars into intergalactic space, and seed new formations elsewhere. Even the elegant spirals of galaxies can be distorted into chaotic elongated flows mirroring the same story written on planetary scales. And yet from this seeming disorder, new patterns emerge. Moons settle into new orbits, planets find fresh balances, galaxies merge into new forms. Eccentricity is not just instability, it's a transition, the bridge between what was and what will be. And one of the most powerful agents of this transformation is hidden in the pull between planets and their moons. The slow, ceaseless dance of tides. A moon is more than a companion in the sky. It is a sculptor of worlds. As it orbits its planet, the pull of its gravity stretches oceans, bends crusts, and stirs atmospheres. These tidal forces are quiet but relentless, reshaping landscapes drop by drop, wave by wave over millions of years. On worlds with liquid water, tides can breathe life into shorelines, drive ocean currents, and create dynamic environments where ecosystems flourish. On Earth, the moon's gravitational pull lifts entire oceans, drawing them into gentle bulges that follow its path across the sky. The planet rotates beneath these bulges, creating the ebb and flow of tides that have shaped coastlines since the dawn of life. Long before humanity, tidal rhythms guided the migration of early organisms and carved habitats along the edges of continents. Life itself rose and fell with the breathing of the sea. But tides are not limited to oceans. They tug on the very crust of a world. Continents flex, the mantle shifts, and energy seeps upward as heat. This tidal heating can awaken volcanoes, sustain subsurface oceans, and even keep a seemingly frozen moon geologically alive. The dance between a planet and its moon is not just beautiful, it is powerful. Tidal forces are born from gravity's uneven pull, A moon tugs more strongly on the side of a planet that faces it than on the far side, stretching the planet into an elongated shape. This distortion isn't just surface deep, it reaches through rock and water, stirring immense reservoirs of energy. As the planet spins and the moon orbits, this stretch shifts and flows, creating a continuous exchange of motion and heat. In our solar system, this effect is most dramatic on Io, the innermost of Jupiter's major moons. Locked in resonance with its siblings, it's pulled and squeezed relentlessly by Jupiter's gravity. That stress is converted into heat-driving volcanic eruptions across its entire surface. No other world in the solar system is as volcanically active, not because of sunlight or internal fusion, but because of tides. Just next door, Europa tells another story. Its icy shell flexes under the same gravitational grip, keeping a vast subsurface ocean warm and liquid beneath kilometers of frozen crust. Without tides, that ocean would have frozen solid long ago. Instead, it moves and flows a hidden sea sustained by nothing more than the steady pull of a giant planet and a precise orbital rhythm. Tides can heat, shape, and even protect the conditions for life. Tidal forces are among the quietest powers in the universe, yet their influence reaches astonishing depths. They can shape climates, sculpt terrains, and determine the stability of entire planetary systems. On Earth, tides have guided the rise and retreat of shorelines for billions of years, creating the ever-shifting boundary between land and sea. That shifting boundary is where life once crawled out of the water, adapting to new worlds with each slow heartbeat of the ocean. The moon didn't just light the night sky, it helped shape life itself. Beyond our world, tides play similar roles. They can keep distant moons geologically alive, maintain liquid oceans beneath ice, or trigger volcanic activity that replenishes atmospheres. Tides can synchronize a moon's rotation with its orbit, locking one face toward its planet forever or gradually slow a planet's own spin as Earth's days lengthen with time. They can even stabilize a planet's tilt, preventing wild climate swings that might destroy fragile ecosystems. But like every cosmic balance, this harmony is delicate. A shift in orbital distance, a change in resonance, or the loss of a moon can undo eons of stability. Tides are both gentle and relentless builders of order and agents of change, and it's at the edge of this balance that the universe shows how easily harmony can unravel. The universe may appear steady, but its balance is never absolute. Every orbit, every resonance, every tidal rhythm exists on the edge of change. A system that seems unshakable can be undone by the smallest disturbance. A passing star, a migrating planet, a shift in gravitational tides. Stability in the cosmos is not a permanent state. It's a delicate truce between forces pulling in opposite directions. Even the most stable orbits slowly evolve. Over millions of years, tidal forces can draw moons outward, shifting their influence. Planetary tilts wobble, eccentricities grow or fade, and resonances slip by fractions. These changes may seem imperceptible from one lifetime to the next, but across cosmic time they can rewrite entire histories. A world once bathed in stable sunlight can tilt into chaotic seasons or drift into icy darkness. This fragile harmony is what makes our own corner of the cosmos so extraordinary. Earth's orbit is nearly circular, its axial tilt stable, and its moon perfectly positioned to shape tides without tearing the planet apart. But this is not guaranteed forever. Even the smallest shift can set the cosmic pendulum swinging, transforming quiet rhythms into cascading disruptions. Every orbital system carries the seeds of its own instability. Gravity, though it binds, is also a restless force. When multiple bodies interact, their gravitational pulls overlap in intricate ways. For long stretches of time, these forces may cancel out, creating stable rhythms. But a small shift, a slight drift in distance, a resonance sliding out of alignment can tip the balance. Once that happens, tiny deviations grow. Orbit stretch tilts, wobble, resonances break. What was once harmony becomes a slow unfolding disruption. This is why no planetary system is truly permanent. A migrating giant can drag smaller worlds into eccentric paths, destabilizing entire chains of orbits. A close encounter with a passing star can subtly distort a system's gravitational architecture. Over immense spans of time, these effects accumulate like tension building in a silent machine, and when that tension is finally released, worlds can shift dramatically, some flung outward into cold darkness, others drawn inward to burn. Even on Earth, stability is not absolute. The planet's axial tilt wobbles, its orbit oscillates, and its moon drifts outward centimetre by centimetre. These changes are slow, almost invisible to us, but their consequences echo through ages, shaping ice ages, altering tides, and shifting climates. In the language of the cosmos, harmony is written in pencil, not in stone. This fragility isn't confined to planets and moons, it stretches across the entire cosmic web. Within star clusters, small gravitational fluctuations can gradually nudge stars out of their original orbits. Over billions of years, these once coherent clusters dissolve into wandering streams of stars drifting through the galaxy. Galaxies themselves can be disturbed in the same way. A single close encounter with another massive neighbour can warp spiral arms, twist stellar paths, and send stars cascading into new trajectories. Harmony can be vast, but so can its undoing. Even the largest structures in the universe carry these quiet instabilities. Superclusters are bound not by eternal bonds, but by the temporary balance between gravity and expansion. In the far future, many will unravel, their components drifting apart as the fabric of space stretches between them. What seems perfectly stable on a human timescale is only a pause in an ongoing transformation. This is the hidden truth of the universe. Stability is not forever. The orbits we rely on, the cycles we build our understanding upon, are part of a grand but temporary choreography. And yet it is precisely this fragile balance that creates time itself, the regular rhythms against which change is measured. When harmony shifts, time shifts with it. Time is not a separate river flowing through the universe. It is measured, defined, and created by motion. Every orbit is a clock, each rotation a tick, each revolution a cycle etched into the fabric of reality. The spin of Earth gives us day and night. The path around the sun gives us seasons and years. The slow turning of galaxies marks epochs far longer than the existence of entire civilizations. Without motion, time as we know it would have no meaning. This is why the universe's rhythm feels so natural to us, because we are born inside it. Our heartbeat, our sleep, our calendars, even the rise and fall of entire cultures are synchronized with the motion of the heavens. We don't simply observe cosmic cycles, we live inside them. Time is the shadow cast by motion. From the orbits of planets to the sweeping paths of galaxies, these cycles weave a universal clock that has been ticking since the beginning. Every world, every star, every galaxy keeps its own time, yet all are linked by the same fundamental principle. Gravity sets the rhythm and motion keeps the beat. Every cycle in the universe is a kind of memory. An orbit repeats itself again and again, carving time into regular intervals. A single day is the story of one full spin. A year is a complete journey around a star. A galactic rotation spans hundreds of millions of years epochs, in which stars are born, live and die, while entire civilizations may rise and vanish without ever witnessing one full turn. Time is not written on clocks, it's written in the sky. The stability of these cycles allows history to be measured. Because Earth's orbit is predictable, we can count years. Because the moon circles steadily, we can track tides and seasons. The beating of this cosmic rhythm has guided everything from the migration of ancient animals to the flight paths of spacecraft. Even the most precise atomic clocks ultimately trace their accuracy to motions we observe in the cosmos. But orbits also remind us that time is not universal. A year on Mercury is different from a year on Neptune. A day on Jupiter is a blur compared to Earth's. And a galactic year, one orbit of the Sun around the centre of the Milky Way, lasts more than 200 million Earth years. Time in the end is local, born from the orbit each world follows. The further we step back, the more the universe reveals a deeper rhythm. Galaxies orbit within clusters. Clusters drift along the filaments of the cosmic web, and entire structures move through expanding space in cycles that stretch across billions of years. These vast motions mark eras of the cosmos far beyond human comprehension. They are the ticking hands of a cosmic clock, whose gears are made of galaxies and whose pendulum is gravity itself. Unlike the seconds and hours we track on Earth, these cycles are not meant for us. A single orbit of the Milky Way around the gravitational centre of the local group outlives entire lineages of stars. The slow ballet of clusters is measured not in years, but in the ages of universes. Time on this scale isn't experienced, it's recorded in the movement of matter itself. Every orbital path is a marker on the timeline of existence. And yet, from the smallest spin of an atom to the turning of galactic wheels, all these motions are connected. The universe tells time through its movement. If these orbits were ever to stop the concept of time, at least as we know it would unravel with them. Motion is the heartbeat of time, and the cosmos is its clock. The universe is not silent. Its language is motion, a vast choreography unfolding across unimaginable scales. Planets sweep along their orbits like dancers following invisible lines. Moons turn in quiet rhythm, pulled by tides older than life itself. Stars trace majestic arcs through galactic arms, and galaxies themselves drift along colossal filaments. From the smallest world to the largest structure, every movement is a step in an ancient ongoing dance. There is no conductor at the centre of this ballet. No hand directs the planets or guides the galaxies. The elegance emerges from the rules themselves, gravity, inertia, and time. Together, these forces weave order out of chaos, harmony out of raw motion. Each orbit fits into a larger pattern, like notes layered into a symphony far greater than any single sound. What we call the universe is not a static stage, but a living performance. Every second it moves. Every billion years it reshapes itself. And through it all, the rhythm never falters. The cosmic ballet is both endless and effortless. A dance that began long before stars were born and will continue long after they fade. Every orbit, every curve, every subtle drift is part of a greater composition. The spin of a single moon is tied to the pull of its planet, which is bound to a star which circles within a galaxy, which moves through the cosmic web. None of these motions exist in isolation. They resonate, forming layers of rhythm that stretch from the microscopic to the intergalactic. What seems like chaos at one scale becomes harmony when viewed from higher above. This is why the universe feels alive. Its motions are not random flutters, but patterned flows, repeating, bending and evolving together like the movements of dancers in perfect sync. The tides of moons echo the gravitational tides between galaxies. The orbital cycles that define seasons mirror the great arcs traced by clusters through deep space, different in scale, identical in nature, and in this shared language of motion lies something profound. Unity. The same laws that shape a grain of dust spiraling in a nebula also guide the turning of a spiral galaxy. Every movement is part of one vast interconnected performance, a cosmic ballet choreographed not by intention, but by the fabric of reality itself. Across all of cosmic history, this dance has never paused. From the first faint swirls of matter in the early universe to the grand spirals of galaxies, today motion has been the constant, the thread stitching every age, every structure, every story together. Nothing in the universe is truly still. Even the emptiest void hums softly with expansion, while galaxies and stars trace their endless curves through the dark. It is easy to mistake this order for stillness, because the cosmic rhythm moves on scales far beyond human perception. Seasons pass, galaxies turn superclusters, drift all so slowly that our lifetimes barely scratch the surface of a single measure. Yet when seen across deep time, the picture becomes clear. The universe is a choreography of unimaginable precision and scale. Every orbit, every tide, every spiral is a note in an eternal song. And this ballet will not end with us. Long after stars fade and galaxies grow dim, motion will continue carving new patterns across an ever-changing cosmos. Just as every orbit belongs to a larger one, every age of the universe belongs to the next. And in that unfolding rhythm lies the promise of the next orbit, the future of a universe that never truly rests. The dance of the cosmos does not end. Long after every star we know has burned out, the universe will keep moving. Orbits will shift and stretch. Galaxies will drift farther apart and new patterns will emerge in the darkness. The rhythm that began at the dawn of time will continue to echo even as the instruments change. This is the nature of motion. It endures. In the far future, the Milky Way will merge with Andromeda Galaxy, their stars settling into new orbits, their spirals reshaped into a single massive structure. Planets will follow unfamiliar paths beneath alien skies. Clusters will stretch and scatter. The great web that binds the universe will evolve, but it will not stop. The cosmic dance does not care for permanence, it only flows. And even when light grows thin and energy fades, motion will remain. Like the last notes of a symphony echoing through a darkened hall, orbits will trace their silent arcs through the cold. The universe will keep turning as it always has, as it always will. Far beyond the span of human history, the universe will drift into a new rhythm. Galaxies will continue their slow migrations, their orbits stretching across a darkening cosmos. Over unimaginable stretches of time, stars will exhaust their fuel and fade into glowing embers. Black holes will outlast them, circling one another in silent spirals, merging in bursts of gravitational waves that ripple through the void like distant echoes. Even in that quiet age, the universe will still move. As space expands, clusters will drift so far apart that their light will never reach one another again. But inside these isolated islands, gravity will keep the dance alive. Dead stars, dark remnants, and ancient planets will trace their loops in silence. It will be a slower, dimmer ballet, but a ballet nonetheless. A universe stripped of brightness, yet still bound to the rhythm that gave it shape. Motion doesn't need light to exist. It doesn't need watchers or stars or even warmth. It only needs gravity and time. And as long as those remain, orbits will continue their endless sweep through the dark, carrying the memory of every world, every star, every galaxy that ever was. In the end, everything returns to the same truth. Motion endures, stars will burn out, galaxies will fade, even light itself will thin into the silence of the void. But orbits will remain faint, slow, almost imperceptible, yet still weaving the fabric of time across an aging universe. Motion is the last storyteller whispering long after the chorus of stars has gone quiet. In that distant future there will be no witnesses, no civilizations, no songs of life. But the rhythm will not need them. It will continue as it always has, a quiet spiral, an endless arc, a heartbeat written into the cosmos itself. The universe will keep its final dance not for us, but for itself. Every planet, every star, every galaxy has its orbit. And when their time passes, new paths are drawn. The dance never truly ends, it simply shifts to the next movement, the next rhythm, the next orbit.